I guess what's like the important topic today is all these like big tech companies on the internet and their power and their monopolization of the internet, and like how hard is it to compete with Facebook and Amazon and so on, like all these guys who own all the tech and data and can really quickly create new products utilizing network effects, and it's really hard to compete with them if you are a new startup or like indie developer and so on. And this state of things probably not comfortable for many people. That's why the whole decentralized web movement exists, when people start thinking how we create new internet protocols, new projects, how can we change this by the new technology. And we like, and you know, this problem is really painful. For example, when you think of APIs concept, like there's a Facebook and Facebook has data of users and they create API, so you can build on top of API, on top of their API new projects. And then Zynga comes up and Zynga becomes so big, they create games, and then Facebook decides that they, you know, kind of compete a little bit with the Facebook itself, or like they just don't like what Zynga do. So they reduce access to their API and Zynga is nearly dead. And there's like a lot of such stories with Twitter API, and many clients and other applications built on Twitter, and then Twitter just shut down their API when they attracted new users with these new products, and then they didn't care. So this state of things prevent innovation a little bit, I would say, like, and keep power in the hands of tech giants. And it would be like really cool if there is a technology that could help change it. And another big problem that is is happening and was really hot topic last year, the cloud versus open source, when the cloud platforms attracted a lot of customers by providing some open source databases and other stuff for users, and then like started generating huge revenues from it, and open source authors were not really rewarded from it. And like people like MySQL founders, MariaDB, Redis, and so on, these guys really could have earned a lot of money. They could have used this money to make their product better and so on. But like all this money go to Amazon, and this consolidation probably not perfect. So with Fluence, with rethinking how applications run on the internet and how they build on each other internet, we're trying to address these issues. And what we do is the decentralized compute protocol and the blockchain-based licensing system. And the idea is we create the network protocol that allows to organize nodes in a kind of decentralized hosting marketplace where you can join the network, run a node, and host applications. You can be professional data center or professional cloud provider. You can be just individual with your own hardware, but the applications can run using the same protocol on different nodes. And we create tools to allow applications to reliably build on each other. So if I created something, you can create something else as easy as possible without rebuilding a lot of stuff. And the idea is you can build on live services. So if I created some live application, let's say Messenger app, you can create a new feature, develop a new feature, and connect it to my service that runs somewhere in the network on some hosting providers, and package it together, the new Messenger app. And this is how you can evolve applications. that's kind of this is how you can basically build faster. You can get to market faster because you not build just on open source code. You just connect to open services that been run in the by network nodes. And the important difference here with the building just on Facebook API, that Facebook API is being run by Facebook. It's controlled by Facebook. It sits on their hardware that they control. And here, if I'm an app developer, I create a useful app and I deploy it to a network. It's being picked up by different hosting providers. So even if someone created another app on top of my app, I will not be able to just cut them off because I'm not controlling the execution of the app that I created. But with business model that we create and which will come later, I will be able to earn revenue from the usage of my useful piece of software in the network. So if my piece of software is popular as open source products like MySQL, and people build applications on top of it, then I will be able to earn from hosting fees for this. This incentive model is essential for all of this to work. It's not yet ready. It's not yet developed. A few weeks ago, we announced the first part, the decentralized compute protocol. So the blockchain part will come later. And today we will focus on decentralized compute protocol and what changed since we announced it, like what materials do we have, what we created, and Dmitry is gonna speak about that. And so I guess I would just Dmitry, you wanna start? I don't know, like if anyone have any questions, just feel free to interrupt us at any moment. And Dmitry, if you wanna start, then feel free to start.
Thanks, Evgeny. Everything okay? Can you hear me?
Yes, we can.
Nice. So we had an event a few weeks ago, the launch event, and let me share a browser with you. Can you see my browser with YouTube?
Yes.
Nice. So last time I had 2 presentations with the slides about our approach to composition that we call Aquamarine, and a very lightweight demo, like how you can use Aquamarine to reuse the services, to reuse the data and users between applications. It's recorded. You can take a look on it. But today, I'm going to speak about not about the concepts, but primarily about the things that we delivered so far that ready to be used right now, and like artifacts that we have. So first of all, we have a documentation. It's on README.io, Fluence Labs README.io. And let's start from the introduction. Just to refresh the main terms of the Fluence network. So first of all, Fluence is the network. It's a peer-to-peer network, open, permissionless, that is intended to run applications. It's built on libp2p. The networking layer is built with libp2p, both for browsers and for servers. This network is designed and is built to provide resources for open applications. And application actually is the user experience, which is constructed from interactions with various services having some data. So application can be decomposed into several services. like in microservice architecture. So we have services. Each service is a set of WebAssembly modules. So we have a WebAssembly format and a WebAssembly runtime to run the code safely. And I will speak more about it later. And of course, to run services, we need to deploy them somewhere. They need to be run somewhere. So we have Fluence nodes, which constitute the network, connect to each other, provide connectivity to end users, and run services. To interact with services, we have a technology called Aquamarine. Aquamarine is a composability medium. It's a way to organize the flow of control from node to node, from peer to peer, browser to browser, calling different services on the way, different APIs, and combining the result as a single object or as a set of events as the effect. It will also be covered later. Then we have some internals like trust graph, which is a cryptographical relationship system. It's inspired by Web of Trust and used to prioritize connectivity. It's implemented. We have it in code, but probably we won't focus on it too much right now. But I will tell where you can read about it. Finally, we are going to make a licensing system and the economy layer using a shared state that requires a consensus and a blockchain. But blockchain is not here yet, so we won't talk about it at all. So that's the main concepts of the Fluence. And now let's switch to GitHub. We have some pinned repositories, and the main one is Fluence. Here it is. Fluence repository contains the node and the JavaScript SDK. JavaScript SDK is written in TypeScript actually, and it will be moved to another repository later. But now it's there. So here we have an image, a wonderful image. Essentially, Fluence network consists of peers running compute engine on every peer with WebAssembly inside. And this part is covered with a FCE, Fluence Compute Engine. The execution is controlled with Aquamarine, which organize the flow, right? And Aquamarine is interpreted with the help of WebAssembly. And finally, we have connectivity, and the Fluence repository is what combines everything together. So we have Fluence Compute Engine that running services and Aquamarine. We have Aquamarine as a service, as a special service, and libp2p to connect everything together. Yeah, and with this code, you also could run a node. Probably you can. How to run a node? Yeah, you can run a node from it's compiled, it's deployed to Docker, and you can join the network as we already have the network. and it's running, and you can see the nodes on the dashboard. So we have developed the dashboard that shows the status of the network. Here we have some nodes. This is Kademlia IDs of the nodes, and they host some services. So it's also available. And you can join the network, but actually running a node and joining the network is not what we expect all the developers to do. Nodes provide infrastructure for clients running Aquamarine. So the primary use case is to run Aquamarine from the client. And also you can develop services and deploy them to the nodes with the help of FCE and WebAssembly. So let's take a look on Aquamarine.
Michi, you wanna speak more on nodes because there's Vivek in chat asks which compute can be a Fluence node. Can I install some Fluence service and become a node for that service? So again, the answer is it's a decentralized network, so everyone can join, everyone can run a node. You can run it on any hardware possibly, and node means it's just like an empty container, and you can host any apps that will be deployed to your node. You can deploy it by yourself. Other people can deploy it to your node. There's also the ability to provide additional external services to Fluence Network. So Dmitry probably will be talking about this. So you can, for example, not only host. So like you can think of Fluence Network in general as a like distributed backend, like distributed microservices backend, but public backend. So it's just a lot of nodes running services. They all connected with the protocol, and applications are the composition of the services. So that's quick description how the network works. And then the nodes can inside kind of Fluence inside the Fluence node software, you can run any applications, any services deployed to this, but also you can provide some external, like some access to API, some external, distributed database, some IPFS nodes, blockchain nodes, whatever. They all can be connected to Fluence node. And it means like after they connected, it means the data from that will be available inside Fluence network. So you will be able to, the app will be able to communicate.
Thank you, Evgeny, for answering the question. Yeah, Fluence is open and permissionless network, and everything we have is open source. So you can join, you can fork, you can do whatever you want. The network is open. But in case you want to run a node, even though you have a tutorial on how to do it in docs, probably you will be one of the first people in the world doing it. So please provide us with some feedback, and we'll ping you when protocol is updated. So about the services, let's take a look on Aquamarine first, and then go to services. Okay. So here we have Aquamarine repository, and this is a simple picture explaining how it actually works. So on the network level, we have a thing that is called a particle. A particle is a package, network package, that contains both script explaining what to do and some of the data collected on the way. Data includes proofs and evidence that some operations were done and some were not. So the particle is coming to the node, either to the node or to web browser, because it works the same way. We are running Aquamarine in WebAssembly natively in the web browser and using our compute engine on the nodes. Here we take the script, which is in AIR format, Aquamarine intermediate representation. It's based on p-calculus. It's just a set of rules, a very simple set of rules that explains the chain of computations, or probably the graph of computations. And on the node, every script, while interpreted, can call services, local services, only local services. These services are running with FCE on the nodes, and it could be anything on JavaScript side in the web browser. Services could be pure, could be effectful, they could be totally like executed inside FCE, or you can run external processes or connect to daemons or do such things. We have some security considerations regarding this. So it's more or less safe. Inside the node, the data of the particle is modified, proofs are checked, and for the new data taken from the services, the new proofs are added to the data. And then the script with updated data, but all other fields are the same. The script and the data is sent to the next peers where the same happens again. So that's the model of Aquamarine. In the repository, we have a quick overview of syntax. It's Lisp-like or WebAssembly text format-like or Clojure-like. We have only one instruction to call function on the local node, and several instructions to explain how exactly to get from one peer to another peer. Like sequentially, first do this, then do that. Or in parallel, do both of these at the same time, or in a cycle. So if it's a parallel execution, for example, then the resulting particle will be sent to several peers, which will figure out what they should do locally and do it. Scripts explains the topology of execution, how exactly the particle flows from peer to peer, and actually the dashboard is done on Aquamarine, and in the log we can see here it is. This structure is what? Is the particle. All these fields the particle has. Here we have init peer ID. It's derived from the public key of the web browser client. We have script as a string. We have a signature, and we have data. Here it's empty. The script is rather complex, so I won't cover it. And AIR, this low-level language that we have right now, is made with a higher level language in mind. So in future, you will have it generated from a higher level language. Right now, it's generated in code. And then we have, from this single script, we have a lot of events from different nodes. So the particle travels all around the network, gets data from peers, then moves this data as events back to the client, and finally, that's what we have. That's what we collected. We collected peers, the services that these peers run, some modules. Wow, 71 instances of SQLite. Nice. And source blueprints, which are available right now on the network. Yeah, let's first take a short look on the code of the dashboard and how it is connected to the network. Here we have it. It's written in Elm because I like functional programming, and the Elm is nice, I believe it. But the connection is done with a TypeScript. It should be there. Should be there. So we generate peer ID. We connect to some relay node that we just know. It's from configuration. Then we provide a service that is called event, and that interrupts calls to any function name from the script. So to deliver an event to the client, you just call a service function for the service event, and function name is the event name. And that's all. The topology is expressed with AIR, just one service for events, and then it's moved to the Elm side. In React and Redux, it should look very similar. And then from the UI, we have data and scripts. We have a helper to build a particle. Here it is. We build a particle from local peer ID, the script, and the data that must be loaded inside the particle. Actually, data is provided to the particle in a sequence of function calls. Particle asks the browser to provide the data from the map. And then a client sends this particle to itself, to Aquamarine that's running in the web browser, in the WebAssembly. So you can see that it's really easy to, for example, copy-paste this code and be connected to Fluence and to play with it. in this repository, if you take a look at it, we also have a helper to, or we haven't. We have. Have we? Okay. Somewhere here. Oh, probably here. Yeah, we have all the primitives of AIR available in Yelm, so you can use call. You can use combinators like sequential, parallel, and XOR. You can express folds, the cycle of AIR from within Yelm with a type safety, which is probably nice. That was about Aquamarine and JavaScript SDK. And yeah, of course, we have documentation for JavaScript SDK. Here it is, JavaScript SDK, build an app, and we have JavaScript SDK. And of course, as you have seen, all the code for dashboard is open. And on the launch event, we had this chat app, blog app example is also on the GitHub. So you can fork it and play with it. It's on NPM.
Dmitry, you want to take some questions about Aquamarine? We also have a few questions about services and nodes. I guess if you will come back to nodes.
The next section is about services, and now it's the best moment.
Yeah. So Pavel. Yeah, Pavel asks. Pavel, by the way, feel free to unmute yourself if you want and talk. So Pavel is asking, have we thought about adding environment variables or symbols vars as enclosure and macros to our scripts, turning it into fully blown Lisp? And why do we need to generate code when you can just macro expand?
Well, what's up, everyone? Is my mic working?
Yes. Yeah, it works.
Nice.
Hey, Pavel.
And
so yeah, I've basically explained the question. So you have like a Lisp-like language, you have S expressions. Why do you need to generate this code when you can like add the fully blown REPL and I guess do the same things that the full-blown Lisp can? I mean, all these macro expansions and like building new DSLs on top of that.
Well, it's one of the options, but right now, this language, this script, is parsed to a syntax tree and then interpreted step by step. And the interpreter is pretty simple. So if we have some sugar on the language side, then we'll have an additional step between interpreting and parsing, right? In this case, yeah, we can have a lot of good things. We can. But finally, we will have this interpreter that takes just one instruction and does a lot of things with it, really a lot, including merkleization, checking signatures, and so on. So the question is, where to have this sugar? And I think that even with the macro style expansion, it would be better to, at least now, it would be better to have this sugar earlier, before the parser could parse it, so that we have a decentralized protocol with a very simple structure of scripts that goes from peer to peer. And we could have a multitude of different approach to add some sugar to the scripts on the client side or with the help of tooling and so on. I think it should be better on this stage. For example, if you take the types of the services, the types of API like function names, argument names, and by default, let's take a look on the structure of call. It's more interesting. So we have arguments, and essentially they are typed. We have a result, and essentially it's typed. And if we take the types, and if we know the interfaces of the services that we want to interact with, then we could even do a GraphQL compiler and compile a GraphQL script very familiar for developers to AIR. Or we can let developers write in AIR. Or we can make a JavaScript-like language that is easier to reason about for front-end developers and that captures some patterns. Or we can make a macro expansion. So these are my thoughts on adding sugar to the low-level language.
Well, that sounds reasonable, I guess. I believe you've just skipped a couple of questions. There is Max who asks, well, his question is, who is the decision, how's the decision made on which node to run the application? So, and the follow-up question from me is, how can you prevent your node from a DDoS attack?
Good questions. Well, probably I won't provide a complete answer to them because it's the huge topic. But in short, you always need to provide a peer ID, and you need to have a distinct peer to call a function on it. But you may use another peer to figure out the next peer's ID. So, for example, you can register your service provider on the blockchain, and you can query the node that you connected to, your relay node, for the most reliable peer, for example. Or you can use Trust Graph and find a peer that is closer to you regarding the trust. Yeah, a long topic. It's in general, it's covered in the paper. We have a lot of approaches for node selection, and it's very close to security considerations and to the economy. And security is not yet delivered, and economy is also not yet there. And that's why I don't want to give too much attention to this topic right now, but a bit later.
Just a follow-up question to my question about how the decision is made, where to run it. How do you want to protect against bad actors, like ones that are logging all your data? I mean, it's probably a really big problem if you have some user data you cannot protect user privacy with user data when running services on that network, or am I incorrect?
In general, you're correct. If you have some user data, actually, I see only two options to store it on the web securely. The first option is to know the machine that you host your data on. For example, it could be yours, or it could be a trusted party to you. And and the same holds actually for computations. If you want to make some computations, probably you need to trust the party doing it. For example, if you run your service on Amazon, probably you just trust that Amazon, and you have reasons to trust Amazon, that hopefully it will be running just what it promised. Another way, if you have no clue where the code is running, is to have some kind of formal verification of execution. Or in case of data, you need to have some kind of cryptography around this data. Like you need to store it in secured way, or if you want to in encrypted way. Or if you need to search on the data, you could use some encrypted data structures and search on them. Or you can have something like...
You mean like homomorphic encryption?
Yeah. You need some very advanced technology, specific technology, which is designed to solve this problem. So I want to say that
you can, if you are running something on your network, you can say only run it on like, let's say Amazon provides hosts on your nodes on your network. Can I tell the network to only run my my services on, or my code on Amazon nodes, for example?
Yes, exactly. That's so wonderful that you asked this question. This is the reason why in the documentation we have this trust graph part, and it was developed several months ago just because of this. And yes, you can ask the network to run your code only on some pool of the nodes that you have some reason to trust to. And when we developed it, we realized that there are many additional use cases for this. For example, you can have a private installation, or let's imagine that tomorrow you want to build an application on Fluence, and you need to have some services and several servers to host these services. Probably you'll have several nodes. And with a trust graph, you can say, hey, you're my node and you're my node. Please trust each other, because I know that you are like managed by me. And if your friend does the same, you can say, hey, my nodes, please trust that guy's nodes, but not the same level like you trust me, because my nodes are closer to me, but a little bit lower, and so on. And you can decide on the right location of different parts of data and different parts of the computation flow, and locate it where it must be, where it can be, where it's secure to place it, and also efficient, because it means that we have data locality.
Thanks, that's answering my question.
Thank you. Any other questions or feedback? So should we?
I have one.
Yeah.
Can we use? Is there any way that CLI can be used in a way of automating processes? Or is there any type of CLI?
You mean CLI for the client? For the
yes.
client side?
Yes.
You can. The node is developed in Rust, and we were supporting CLI. I think we were supporting. I'm not sure that it's stable right now. Yeah, and the browser part is written in TypeScript, and it is almost running on the Node.js. There is one bug that should be fixed. So probably, I'm not sure that it's running right now, but if you need it, let's discuss it, or you can just fix
I
it.
feel like CLI would be a great thing for like automation, you know, especially on something like certain type calls that would be repetitive, like if it's large files being accessed, little things like moving data, because like you were saying, like checking signatures. Let's say if I wanted to create a process to create a public record of like to tokenize signatures in a way of showing proof of having access to something, you know. And I was just looking at that as an actual solution to build on top of this and also have it embedded, you know, at the, you know, at the node level as client.
Speaking about the CLI, we have you can run or you will be able to run CLI client for the Fluence network. And it means that you can send particles, send the scripts and data, send requests to the network. And this is the first case how you can use Fluence network, integrate with it from the outside. There are also two more usages.
Yeah, I think the CLI would be the better usage based on, you know, what people are somewhat now accustomed to in cloud and working with hybrid cloud and things like that. You know?
I want just to maybe expand the perspective about the services and services with the CLI. Where should it be?
And that's another thing also with CLI. I see that it'd probably be great to use CLI based on a lot of the devices that's like in IoT and edge computing. And I feel that this would be a great, beautiful thing because you can basically just run everything from hardware. Let's say like you were saying earlier about DDoS. I know from that functionality, that's something that also can, at the hardware level, you know, say if it's, I'm trying to make it in layman's term in a way of something simple, like an actual network that could be like a private network. Like you can go from public to private, you know, also.
Yeah, it's definitely the wonderful use case for all this Fluence choreography approach.
Oh yeah, I see it now. Yeah, FC. Okay. Oh, cool.
I just want, yeah, probably I want to switch to services. Or is there any other question? Or maybe I will cover the services part a little, and then we have...
Pardon for interruption, but I guess you've missed a question by Jeremy Helm. He's asking whether Fluence apps would be able to integrate with HoloChain, whatever it is.
Yeah, I will answer this question during discussion of services. I want to speak about services. We really need to introduce it. So let's get to services. Okay, how it sounds. So all about services is the FCE world. We don't have a lot to read there, but here's the repo. Probably we should have several talks by Mike recorded. I hope he's giving a lot of talks. And we have a lot of documentation on services. So a service is what can be deployed and called. And each service could be decomposed into modules. Modules could be used in several services. So we have modules. Module is the result of a compilation to WebAssembly target. From modules, we build a service, and we call several services with Aquamarine composition all the way. The wonderful thing here is that we have several types of services, of modules. We have pure modules that just execute WebAssembly code and does some pure logic, like take this, put here, or something like that, +1, inverse, concatenate, and so on. This is just sandboxed, like WebAssembly is quite isolated and efficient computations. Then we have facade modules, which expose API of the entire service to Aquamarine. There is no other way to call service except Aquamarine. And finally, we have effector modules. Effector modules can access file system through WebAssembly system interface, and also it could call external binaries. So if you have your private database, or if you want to access IPFS data, or if you want to integrate with a HoloChain, or if you want to deploy, if you want to have like 20 nodes on Fluence connected to each other with a Tendermint or something like that, you can just do it. But in this case, you cannot just deploy the effector module on any node. This is a violation of security. So you will either need to have your own nodes running HoloChain, for example, and running effector modules which connect to HoloChain and provide HoloChain data to the Fluence network, or your private Tendermint cluster to Fluence or IPFS. Or you can somehow make hosters, make node providers provide this effect and run. What does it mean to provide the effect? It means that the binary must be accessible and the module must be considered secure and registered in the node so that it's available for use inside the services. And if you take a look on the dashboard, for example, we have URL downloader. And the URL downloader uses CURL. So it's a binary which is called as a CLI on the node. And you can make external calls and fetch data from any URL with the help of any node that provides CURL module. This module is wrapped with a facade module and provides URL downloader. So just give the URL, download it, have it as have the result as JSON, and then manipulate it with Aquamarine.
And also, I guess, addressing the question from Mehmet about do we have any plans to execute sensitive code, security verifiable using Intel SGX or something like that? It can be done the same way. So the Fluence protocol itself is like more general. It doesn't provide you like blockchain consensus or multi-party computations and like security. This kind of security. You can have a node that has Intel SGX, and this node can be also Fluence node. So like you can have Intel SGX on some machine where you have Fluence node, and you can create the module, the adapter to the interface to Intel SGX, and then do and allocate some execution there. That's basically the way to connect to any external thing. And also, like you can, I guess, if there are few nodes in a network that have, for example, Intel SGX, or a few nodes in a network that have access to IPFS, like run IPFS node, or holochain nodes. I maybe don't have full understanding how holochain works, but let's imagine this is similar to peer-to-peer network similar to IPFS or blockchain, let's say. So if there are few nodes in the Fluence network that also run in nodes to another network, then on Fluence network you can select, basically you can choose between these nodes. You can write a Aquamarine script saying find me nodes providing IPFS, or find me nodes providing Intel SGX computation, and send this data to them and get a response somewhere. So you can do all of this with Aquamarine scripts. You can discover whoever provides what external service.
Thank you, Evgeny.
Thank you.
Here we have this table is in the Fluence repository. I like this table, probably, yes. And here we have different layers of coordination. So for execution, we have coordination on the single peer. But what we coordinate on, it's the state of the disk, maybe a network call like CURL, and its external processes. And this means that you can have the effects of probably anything which could be considered as or thought of as an external process from a single node, from a single peer, including Intel SGX and other networks and IPFS and so on. We have so many solutions actually for different problems, and we decided not to try to solve everything for everybody, but instead to provide a way to compose the effects of these networks or technologies in a decentralized way. So I want to end the part about the services. If you want to develop a service, you have the section in documentation about creating a service, and it describes how to use WebAssembly, how to make interface types, how to link modules with each other, how to make the API. We have some tooling to do it. Some of this tooling is made for Rust. We have Rust SDK. We have a read, eval, print loop for services. So you can test your service as a whole locally. So, and we have docs on deployment, on running a service locally and on deploying a service. So you can take a look on it. And I want to sum up on the code side. Oh, let's get back to the GitHub. So here we have Fluence for the node and also the JavaScript SDK. We have Aquamarine, which compiles to WebAssembly and is running an interpreter for the low-level AIR language that describes choreography. We have FCE, Fluence Compute Engine, that runs multi-module WebAssembly applications or probably services with interface types and shared nothing linked scheme. We have two examples of front-end applications. It's Aqua demo with this chat and post from the previous talk, and it's the dashboard that I showed just and which is available on dash.fluence.dev, and it's also running with Fluence. We have some more code here, like Rust SDK, and maybe something also interesting. Just take a look on it. And I suppose that it's enough to give Fluence a try, because all the main moving parts are ready, open sourced, and explained in documentations, and it has examples. Yeah, also we have examples of services in FC repository, so you can take a look on it as well. But in the future, we have a lot of things to do, and that's why we published the overview and made the RFC's repository. Here we have the overview of application design. What is application? What does this recomposition mean? Then Aquamarine with some vision of higher level language. Then some explanation on authorization. Authorization will be encoded in the following weeks. Flow of AIR processing, and a lot of things which are required but actually are under the hood, like network overview for trust graph, DHT, and yeah, service. So actually just, yeah, it's about trust graph. Now you can take a look on the vision where we want to move. And I hope that in the following weeks, we'll have more documents here in the RFCs section, because a lot of research is already done and is in progress right now. So thank you for your attention and your questions. That's all on my side.
There is one more question in the chat.
Yeah.
It's about basic requirements on creating a node. And the question is whether a node can be cloud-based. Yeah, sure. All the nodes you see currently in the network are cloud-based. You can use whatever computer you like. So if it has an internet connection, can run Rust can be compiled to that architecture, and WebAssembly can be run there. So yeah, you can use anything.
Probably, thank you, Alexei. Probably the only restriction is that currently to run a node, you need to have a publicly accessible IP address.
Or if you don't have a publicly accessible address, you can always deploy your services behind the relay. So
yeah,
you can use
just like the clients.
Yeah, just like the clients. You can use one of the existing nodes as a relay.
Mm-hmm.
And if you're curious to try run Fluence node on any hardware, just feel free to do it and give us any feedback. We haven't tried to run it, like we tried only in the cloud, so it would be awesome to get some new information from different types of hardware.
Evgeny?
Yeah, so I think if there are no more questions, I can sum up. Let me try if I can share screen quickly. Okay, awesome. So what I wanted to add just quickly in the end, that we are looking for new people, like new additions to Fluence team. We have few positions opened, engineering positions, developer, evangelist, UX UI designer. So if you're interested, feel free to reach out. Everything we do is open source. So we are open source project. We are a distributed team. We are remote first culture. So if you like that, then I think we should talk. Reach out to us. And a few other things. So we have links to these example applications that Dmitry mentioned, also from documentations. There's example of how we convert chat application to blog platform easily with Aquamarine that we've shown last time on launch event. And there is also links to repo and to network dashboard. And we have this page containing all the important links to paper, to proposals, to key repositories, network dashboard, JavaScript SDK to build apps, Rust SDK to build modules and services, GitHub discussions, Telegram group, Twitter newsletter. Feel free to subscribe anywhere, feel free to join. And also like GitHub discussions. It's a new feature, I think, at least for us. So we have 0 discussions right now. We just opened it. So feel free to write anything there. Yeah, we've got some Fluence swag for, let's say for first discussion on GitHub. I don't know. We can decide anything. Just yeah, if you're interested, try to play with this. Go to network dashboard. Try to break it. Try to run some Aquamarine scripts in console. Play with it. We really appreciate any feedback. That really helps. Yeah, and that's it. I know if there are any other questions, I think this is time to ask. And if not, thank you everyone for joining us today. Nicholas saying that would be dream job, but he's already busy. It's sad. What could we say? But you can always contribute any other ways because it's open source. Just feel free to open issues, open discussions, ask questions, try something, we are welcoming any contributions.
Hey, I have one question. I just wanted to get see if I can get more information on the CLI information.
Probably we should have some place to discuss it. Here's Alexei, for example, one of the core developers, and I suppose Alexei was making the Rust SDK, right? Sometime, or at least it's a nice person to talk to about everything, including CLI tool for Fluence. Let's discuss it and take a look on the code after the call. You can leave your contact, for example, or join our Telegram group, or open this GitHub discussion, and we will show you everything.
Okay, great.
In the code.
Okay, Nicholas saying he was working on Holochain. Yeah, but anyway, feel free to check out Fluence as well. Awesome, guys. I don't know. We can just sit here and look at each other, or let's go and have some dinner, probably,
or breakfast,
or lunch.
Thank you.
Thanks, everyone.
I hope to see you on the next call as well. Bye-bye.
Yeah, join our next calls. Thank you. Bye.
Thank you. Bye.
Bye-bye. Thank you.